Welcome everyone to another OCP tap call. This is call number 131. Today we have Professor Ken Bierman giving us a presentation. Ken Bierman is the Rama Rao Professor of Computer Science at Cornell University. His work seeks a balance between protocols and strong guarantees and practical utility and efficiency. His earliest distributed system work includes the ISIS toolkit, which plays many roles in the French air traffic control, active without a single outage in 1995, and was also used to run the New York Stock Exchange trading floor and the Swiss Stock Exchange as a basis of a command and control system in the US Navy AEGIS and many other critical systems. Later work explored gossip protocols and reliability and consistency in cloud computing infrastructure. He has a long history of entrepreneurial
All right,
activities.
enough of the intro. You're
Sure.
using up all of my time on it.
You have time. We have it recorded. I
Oh,
mean,
yeah,
just
we have
last
enough
part,
time,
right?
except I have to go pick up my wife from an airport an hour and 15 minutes
All
from
right,
here.
no
I
problem.
have to
So
leave it on
the
time at
floor is
3.
yours, Ken. Go for it.
Okay, thank you very much for the long intro. Okay, so and since this is the tiny group, I'm also going to on the fly adapt this talk a little bit. So I want to talk a little bit about work that a few of you have heard of once or twice, a system called Vortex. It's a new architecture we're building for accelerating ML inference and knowledge retrieval. And we come at this as systems people. So the question that I was interested in when I got involved, kind of question that Pat Healand would ask, is how systems people interested in time should think about machine learning. Are there aspects of machine learning where timing properties of a system are very important? Which timing properties? What about, there's obviously going to turn out to be situations where latency is important. Are there situations where clock synchronization is important? What about temporal properties like causality and consistency, which we generally define in terms of notions of causality? Do these have important roles in ML systems? So I want to tell you about Vortex, but in the back of my mind, and hopefully your mind, will be these questions. And what I'm going to show you is that, in fact, every one of them leads to very, very interesting insights. So, ML, I don't have to say much about it. It's showing up everywhere. This is an example that was given to me by a friend at Microsoft who works on machine learning for farms, farm beats, it's called. And so, of course, farm has cows, but the kinds of questions that you may be asking could involve understanding river depth and whether flooding over the next couple of months might prevent you from using certain pastures, whether mold is breaking out, and so you can't use the pastures because perhaps the alfalfa is going to be damaged. And that might involve purchasing expensive satellite imagery. You'd like to purchase it if you need it, but you don't want to waste money on it. And each one of these aspects could involve cooperation between a bunch of MLs. So MLs could learn about the performance of cows under different conditions. But to predict the depth of the river, you're going to need a prediction of the upcoming weather. And so you end up with a data flow graph with a variety of input nodes. They could be things like weather prediction or satellite imagery. And then the edges would represent data being moved. They could be data objects, audio, video, photos, other types of modes of data to nodes which aggregate and integrate and try to draw some form of conclusions. And eventually, we very often would have a human being interacting through voice or through text and asking sensible questions. Could see such things in other settings. Another Microsoft example, completely a fantasy right this minute. HoloLens obviously couldn't do very much for servicing equipment because you can't have a hot computer with a GPU on this poor woman's head. However, it could be connected to a set of servers, And so if you start to think in terms of a small cluster somewhere that's integrating input from many sources, she's really just using a visualization tool. Now you can start to imagine that she says, I hear a vibration. It highlights a pipe and says, touch whatever that wand is to the pipe, and checks to see if that's the primary vibrating source. And maybe there's a loose connection. Medical examples come up, and we hear about them all the time. And again, you could have quite an elaborate collection of AIs involved. And think about this doctor and his patient who suddenly has some sort of a shoulder or a rotator cuff issue. Patient wants to raise their arm. You've done imaging. You'd like the AI to highlight the nerves that are probably being pinched or whatever the hypothesis might be in real time, superimposed on the patient's body and on the cervical spine, aligned the way it is with the patient sitting right the way they are right now. Each one of those would potentially be an AI. And these AIs are getting embedded in all sorts of things, right? So we're in a world now where co-pilots, this of course is still Microsoft, I could have used Google, Amazon, anybody, where co-pilots are showing up everywhere. So as you work, a co-pilot is continuously monitoring what you're doing on software development or producing a PowerPoint or whatever it is you're doing, continuously querying an ML data flow graph like the ones I was showing you, and continuously making useful suggestions, or at least you hope they're going to be useful. And I find, by the way, that for software development, they're becoming already very useful. So you have these pipelines, these graphs, and the graphs, the nodes are individual AIs, each one with its own machine learned model. Those models could be very, very large, each one doing a different task. You may have heard the term mixture of experts. That's not what this is, but that would be another kind of data flow model. That particular case involves separate AIs, but also with a weighting function superimposed to in some sense, say that, well, for this electrical engineering task, Ahmad is the local expert, and I should trust his perspective. You can do the same with AIs. But these graphs are simply feeding AI inferences or knowledge stage to stage. If you're dealing with language, you would often take audio and turn it to text if you had audio. You would take text and run what's called a transformer, performing a task called attention on that. It's an autoregressive activity. With document and query embeddings, what you typically do is you take documents and you break them into chunks, and then you generate a numerical vector, very often a thousand dimensional vector. And that vector is going to represent the information in that query or that fragment of the document. And you can now sort of talk about having little paragraphs which caught the attention of the transformer, having a representation of that information that points to the paragraph and points to the real document. We can cluster these things and form nearest neighbor clusters. And now we can think about an approximate search where you query the system, it finds the document fragments that come closest to your query, looks for a diverse sample among that set, because there may be many, and it's an approximate match. Enlarges the prompt and generates a response, or the knowledge may be exactly what we were looking for. So if I'm apparently building a doubly linked list, one of those documents might be a good implementation of a doubly linked list in C++, and the copilot could say, it looks like you're doing a doubly linked list. I have an implementation. Would you like me to use it? If it's text and we're generating a response, we might have an extra AI checking for hallucinations. And so, we see pictures like this all the time these days. In fact, people are building these kinds of pipelines all the time. And in fact, more and more, they're beginning to work with what are called foundation models, where the huge expense of training the initial model is done by some big company, and then they share out the foundation model that they generated, and either for free if it's open or for some sort of a fee, you can use it as a component in your graph. Some places, like particularly Meta is famous for it, they actually give you the model. You can run it locally. Others, they want to serve it on their own cloud. Either way, it's a component in the graph. So this is the kind of picture that I have in mind. And the question that we want to start by asking is there an opportunity for systems researchers to make this world better for the people building these graphs, for the graphs as they execute, and for the owner of the platform, right? The owner of the platform has a monetary bottom line. Should I put a GPU on it? How expensive a GPU should I put there? How busy will it be once I buy it? Does this cluster need RDMA, ROCE, which is a version of RDMA on Ethernet, or true RDMA? What's the cost benefit to me of that investment? So it's a world that's very financially driven, right? The second people have the view that they're investing to get kind of territory in that space, but over time, the costs are so high that they're going to shape everything. And as a systems person, that gives me an angle. I can come in and say, well, maybe I can drive those costs down through systems work at the operating system layer, speed up these kinds of pipelines, and cause your cost of ownership to drop. And I should mention that individual components could themselves be distributed programs. So just a random example. It's a what's called a visual language model, a VLM system. This particular place went VLLM, but in any case, VLMs have a photo and a query about the photo. Okay. What tree is this that's flowering? How many other people are allergic to it? And is there a recommended product for not sneezing constantly when I give my talk? Things like that. Now, these platforms are often coded in a diversity of languages, and it's especially true when you see multi-component solutions. So when I show one of these graphs, you shouldn't assume that it's all PyTorch, all TensorFlow. There are tons of different systems. There are languages emerging just for this purpose. Julia is a popular one. And so what we really would like to do is say that much like we can build pipes on Linux, take the output of one and pipe it into the other, and I don't care if one of them is Python and the next is C++, really we ought to have a similar kind of capability. Even within something like Python, it turns out that major libraries like NumPy, Pandas, there are all these different libraries. Some of them only work at certain rev levels of PyTorch or Python. You can't combine them if they need different revision levels because the component has to be extended or retested or whatever it might be. If we had a very componentized perspective, we'd be able to say, well, it's no big deal. We're going to run them separately, and they can just talk to each other, and as long as they agree on the data formats. Right now, that doesn't actually happen. We'll get more to that in a minute. So how do these ML pipelines differ from web microservices that you might see on Amazon or any other big hosting company? So first of all, the MLs themselves tend to be built by composing components together. Now, I should be honest and say that the majority of MLs that people run into today are built that way, but then they are bundled into a single program, a container basically, that ends up running on a single server. So even though the structure internally is of a graph or a pipeline, the execution entity is just a program. Now, that's quite different from web microservices, which are deliberately built with clouds of little services, and you talk to AWS, and it farms out pieces of your web page construction to 100 different processes, which may in turn talk to another 100. They're not as elastic. Now, with web microservices, we think in terms of highly elastic behavior. So Amazon operates maybe 10,000 front-end servers on a given data center, and dynamically, the number of instances of any given web microservice that's in their tremendously large collection will vary based on whether it's in use at all, then it'll be down to 0. Whether it's in heavy use for some reason, then there might be 5, 10, 100. And they dynamically change that all the time. So we call that elasticity. ML models, though, are huge. An ML model could be hundreds of megabytes, often gigabytes. Some of them are hundreds of gigabytes. If you want to spin up a new instance, you're going to have to make sure that ML model is on that machine, loaded into its GPU very often, and that it's kind of ready to go. It's not just a question of launching a little teeny piece of Python code. And then these are also models where an event comes to the beginning of the pipeline and then it progresses to the end of the pipeline. People are much more used to a web services model like fan out back, a collection of concurrent RPCs, get the answers, render the page. All of which adds up to it's a microservices problem, but the existing microservices platforms won't be very good at it. Now, similarly, there are a tremendous number of products for just ML hosting. And these products, it's interesting, turn out to have, on the whole, evolved from ML products for ML training. And the main reason for that is people have done decades of ML training. We're only just beginning to have MLs which really work well and that we are concerned with deploying and hosting this way. And so the quick way to get an ecosystem up and running, and also a friendly, familiar one that your developers are used to working with, is just to take the training environment and turn it into an edge environment. It's edge meaning the part of the cloud that deals with external requests. So you may have had a system like Ray, very famous ML training infrastructure. And now there's RayServe, which is a specialty version of Ray, tuned, partly re-implemented for these kinds of hosting tasks. When that happens, assumptions that originated in the old infrastructure often live on. And one of them is a broad philosophy that when you're doing ML training, you don't worry about latency. You focus on high data rate, asynchronous pipelines of work that flow through the system. And by and large, your system is so decoupled that the amount of time it actually took isn't really the issue. The issue is the efficiency of your pipelines. So viewing an ML pipeline as a component graph, as a collection of components, is a new thing. It's not a new thing that I'm inventing, but you'd be surprised at how few of today's hosting environments adopt this perspective. And Vortex will adopt a componentized perspective. So if we're looking at a standard ML that was already built and trained, we might still decompose it into components and break up the model into submodels for the different components, which is often the way they are implemented. You think of them as having one model with a billion parameters. It really turns out that it's a collection of MLs in a monolithic packaging with 5 models internal to it. So breaking them up isn't hard to do. Or you might build one from scratch using foundation models. So the idea then, Vortex, is to build a distributed service, a framework that can host these MLs and actually the data they run on too, because co-location of the execution and the potentially big data objects could be a very big benefit to you. So co-host data and execution on the same set of servers. And we're going to try to make this extensible so that this server infrastructure becomes your microservice, your ML inference and knowledge serving microservice framework. And then each one of these different user-defined extensions can benefit from the overall behavior of the framework. So that's what Vortex is about. It's actually built in pieces. One piece I gave a talk on about a year, well, maybe less than a year ago. It was probably 9 months ago. And that's a system called Derecho. It's a RDMA-oriented, ultra-high speed data replication, coordination, and synchronization framework. It's in C++, open source. Other people can use it, and we use it ourselves. On that, we built a standard data hosting layer, what's called a key value infrastructure. It just holds data that has names. The keys are names, the data are bytes in a bucket. And we call that layer Cascade. I won't talk much about Cascade today. And then Vortex is actually layered over all of that. It's much more recent work, and it focuses on all these categories of MLs and also focus on cases like what are called retrieval augmented generative LLMs, which are large language models coupled to a database that they interrogate in real time as they respond to your query. And typically what that database is used for is an approximate search that finds pieces of documents like I talked about before. That example I was giving was a RAG LLM. It's a vector database. And so Vortex supports vector databases and other kinds of functionality that add up to these composed pipelines. So let's have a look at what a Vortex server is. Now, as I said, Vortex itself is a runtime framework, and you typically run it on a set of servers. It might be a very large cluster. It could be a small data center. It could be a small cluster. And so this is an example with 9 nodes and then others implied. And each of those 9 nodes is holding data. So this is going to be the cascade portion of Vortex. And when we talk about a key value structure, key is a name. Again, the value is one of these pages of yellow. You can fetch and it'll look for that object for you and find it and return it. And you can put objects in. And the idea here is that to make these things very scalable and very fast and predictably fast, what you do is you take the key, you apply a hashing function, the name, you take the name if you want, and apply a hashing function, modulo the number of, we call these shards. These shards have 3 servers with identical replicated content. Any one of them could be getting documents for anything it hosts. All 3 of them have to be updated in a coordinated way, using, in fact, atomic multicast, if I do a put. And so anybody who knows the hashing function and is trusted can RPC into one of these members and either initiate a put or do a get. And I should just very, very briefly mention that a key value term also arises in people who work with LLM transformers. They have a QKV representation, and they mean keys and values, but not in the same sense. That their keys and values are large matrices. And Q is also is the query. It's a matrix representing embeddings. So the QKV objects could be put in this, but that's not really what KV means in this context. Now, so let's extend Vortex with your ML. What you do is you package your ML in something that Linux people call a dynamically loadable library module. Java has things like that. Python has things like that. And we supply a wrapper for this, meaning a framework just for the DLL. And your component, instead of running as a program all by itself on Linux, or inside PyTorch, for example, would have TorchServe, your program becomes a part of our service. What we do is we literally load it into the memory of our servers. And we actually load the same code in all of our servers. So if you want to provide an extension that turns Vortex into a smart service for predicting weather, you would build the ML component for that, and then you'd supply it to us. And all of our servers, the 9 in this case, can run that piece of code. They might not have the model in memory. Picking one that does have the ML model in memory will make a really big difference for performance. But all of them kind of have the same functionality available. And you can extend this with RAG LLM components like approximate vector search, vector database search, prompt formation. All the things I was talking about before can be DLLs. And we can have many, many of these extensions all at the same time. We have to trust them. They're all going to be in the same address space, but the argument here is that we're going to be trying to drive costs down. So that's not going to be a bad thing. We want to avoid copying because copying is slow. Okay. So if you look at a pipeline, here's a pipeline, typical kind of pipeline. We do experiments on this particular one, actually. It's for asking questions about images, such as, is this type of dog a good choice? You're over at the SPCA. You have text, which maybe was rendered from your audios, from your speech, and then you have the image itself. Encoding, if you remember, is the transformation of inputs to numerical vectors, often very large vectors, 1,000 dimensions or more possibly. And they use one address, one vector space, even for the images. And so, in fact, you have a text encoder and a vision encoder. And then you do something called cross-attention, where you focus on the aspects of the vision of the image relevant to the query and end up with another encoding, which in this case becomes the input to one of these approximate nearest neighbor searches in a document repository, which happens to have knowledge about dogs, hopefully. The particular one I'm showing you here is something called pre-FMLR, and it's part of a question and answer system, which is quite popular, very, very effective, and it's open source and free. And what we did is we downloaded it and split it back up into components. So this is one way to make a componentized system. Another is to take foundation models and compose them together. And we did that as well. So we ended up with two pipelines representative of what we believe people will work with in the experiments that I'm going to tell you, among other things, use these pipelines. The second one was similar, actually. They were all sort of similar, but they often have specially trained models. So for example, the language a doctor would expect to see is specialized for, what that doctor does, orthopedics or obstetrics. They would expect to hear certain types of language. If somehow a document snuck in that had inappropriate or problematic language of other sorts, they'd rather have that filtered out. That's what NLI does. And so you have similar structure. The queries come in, you encode them, you do some sort of an approximate nearest neighbor search, which might be a hierarchical cluster. There are a few ways to do it. And then you take this collection and you could talk about the documents directly if that's what the user wanted, or you could feed it into a generative LLM and it could compose a little essay. Okay. So this is the Vortex development process that I've just talked about. Create the componentized pipeline, turn the components into a DLL, decide how you want this mapped onto the service pool, because different components may have different specialty needs, like different accelerators. And we actually use tools that assist in this process using optimization techniques. And what we'd like to do is to pack the GPUs to be as busy as possible. So multi-tenancy on the GPUs. Since it's a multi-component system that we're treating as a microservices architecture, a monolithic deployment would just package it as one instance. And if you had 4 servers, you'd run one instance each, or maybe 2 instances each. We can decide how many instances we need of each component and vary that based on the component's performance profile. So we do that. So let me tell you a little more about Vortex itself. So what is Vortex really? It's a program that can run on 1 to large numbers of servers. They link to each other. They make RDMA connections if RDMA is available. And then they have infrastructure support for the key value part, plus an application programming interface, which is offered to those DLLs. So it's kind of a universal runtime, and it's intended to support all these different AIs side by side, with partly the intent that if one AI talks to another, we can pass a pointer if they're in the same address space. And we can use RDMA and get a zero copy effect where at least we didn't do any copying if they're on a different address space, on a different server. It needs to be very back compatible, and it really is. Porting an AI is not hard to do. And now we can finally start to talk about time. What we want is for this architecture to use the hardware very effectively by virtue of having fragmented this monolithic thing into pieces or just built it in pieces in the first place. Let's map it to the hardware to keep all elements as busy as we can, maintain high throughput, which is the sort of universal goal in this world, but also get very low latencies. And even, support things like dynamic updates with strong consistency. And I'll show you a consistency example in a moment. I already told you about UDL, so I don't have to say more about that. And I actually don't really have to talk about this either. Let me just show you a picture. So let's suppose that we are doing the medical one. The doctor has some sort of image capture device present, and it caught this photo. It's going to upload it. Now, traditionally, in a cloud, when you upload something like a photo, it actually goes into a separate storage layer. I mentioned earlier that Vortex doesn't work that way, but the standard cloud has its own file store, which might even have sub-file stores. This would go into what's called the binary large object store, the blob store. Then you have your AI, which is probably running in PyTorch or running in TensorFlow or something. In a deployment environment, it could be TorchServe, it could be Ray, it could be one of the others. Your little piece of code is just a tiny piece. That infrastructure is pretty large, and it's probably GPU accelerated. And so what's going to have to happen is that in order to ask a question, like this doctor's question in red, the AI is going to really have to fetch the image from a file store, pull it over, and maybe other objects too, maybe the ML model for that matter, download that stuff into the GPU, and only then can it do its step of this computation. And this is a very lucrative business to serve this stuff because AI has become the big business. But it's got a lot of problems, and I mentioned them all along the way. The data paths are optimized for batch processing. It turns out high throughput, not real time. I'm going to show you an issue with noisy data in just a second that would be visible to a doctor. It's hard to support AIs that mix components, but people increasingly want to do that. So what we're going to do with Vortex, back to our picture, assume this is the Vortex server extended with lots of DLLs, is we're going to be able to support that same AI. It's actually in a DLL, although we have a way to run it in a container. The objects Vortex manages are in a pool that it's allowed to see. However, it goes through our APIs, and it's not supposed to trash that pool. We trust these things. It's selective. It's reasonably secure. It's not designed, though, for partition security. And we can cache various objects. So if we realize that this particular use case needs a particular model, we can try to keep that model right in the GPU cache. And in fact, as the image comes in, we can use hardware paths, something called RDMA Direct, for example. If it's NVIDIA, Intel has paths like this too, Intel Fab Service in the Intel Fabric architecture. And we can try to move our data directly into the GPU that's going to compute on it, selecting a GPU that has the correct model cached and that has the dependent objects that it might need, like a database, so that when we get that question, we're immediately starting to perform the task. And when the stage-to-stage handoffs internal to our architecture arise, because this is microservices and we're trying to treat them that way, we want very fast handoffs. Well, they are. For sort of typical object sizes for moving from one stage to another, 33 microseconds in a case of a 100 gigabit network. And a throughput could be saturating that network, but 8 gigabytes per second out of 12.5 theoretical is really pretty good. Right? That's 100 gigabits. And by the way, 100 is kind of slow. These days, you can easily get 400. 200 is very common. So these numbers, I should rerun them actually. The latency won't drop much though, because with Rocky, you've got a transfer from electrical to optical and back, and much of the 33 turns out to be that transition. Okay. So consistency matters too, but let me give you an example. It's a real example. We had an opportunity to work on the smart power grid, the bulk smart power grid for the region that's in this box. New England ISO is the regional big player, the RTO, and they coordinate the power grid even with interchanges across to their neighbors in Canada, in New York State. There's a gigantic transmission operator that runs from Canada straight down to New York City. And all of this infrastructure is increasingly trying to be smart about shifting power around and allocating it efficiently and coordinating pricing. Now, the way you monitor a power grid is you take a sensor, it's called a synchrophaser. It's synchro because it's got extraordinarily high quality time from GPS sources, and phaser because it's going to measure the phase angle of the power equation. Okay, and so that's you know power spirals, if you want to think of it that way, has an imaginary component, and it has the real component that we see as a sinusoidal oscillation. That's really a projection, and the imaginary component corresponds to a spring effect. That when power is pushed into a cable, it's exactly like springs, okay? And that gives us this effective alternating current. So synchrophaser turns out to give you absolutely exact characterization of the state of a power grid wire, a bus, at a given location. And what we can do is take a kind of a matrix. Now, I'm simplifying because it's easier for the photo, but we can take a kind of a matrix, and we can take the synchrophaser corresponding to a particular region, to the bus really, and we can store that, and then we can have more synchrophasers. And now we begin to get visibility of the state of the power grid across the set. Now they're capturing data at a pretty reasonable rate, where we capture data at about 20 snapshots, events per second. Okay, each one with a high quality timestamp, and each one with the corresponding phaser. It's a small object. So what these arrows represent here is data streaming in at 20 events per second. And the real grid has a lot of elements. And then we can start to do things with that. For example, we could make a snapshot and visualize some property that has a visual representation. I'm going to show you one in a second that involves the phase as somebody turns on a gigantic solar farm. It causes a phase shift, and we can see it ripple through the grid. The ML might not want to visualize it, but it could sense the identical thing and then react by saying, hey, don't trip all your, they call it tripping a line when you turn off a line. It could pass the word, hunker down for a second, there'll be a phase shift, don't trip any wires. For the visualization, I'm going to show you we don't really need 20 frames per second. We're going to step it down. We'll use 4. And you want to do it in real time, right? I mean, you don't want to know what the grid looked like 5 seconds ago. You want to know what it looks like right now within milliseconds. Because if you're dampening the grid to brace for something, well, those disruptions move at the speed of sound. Speed of light's faster, but not if you waste time, right? Now, so here are 3 representations of a phase shift propagating through our grid. This particular rendition is 20 by 2400 synchrophasers. There's redundancy. It doesn't really look like the power grid because they didn't let me use the true circuit diagram, but anyway. So what differs? On the left is what you get if you use a standard cloud platform using Apache's standard Hadoop file system. As you can see, it looks like garbage. And you got to really ask yourself, if an AI is fed garbage, is it going to react right? I mean, think about all those cars, the self-driving cars that run into each other or run into people. We read about them all the time. what did the AIs really see? I mean, they always show us what the dashboard cam saw, but what did they see internally? If you think about it, what you're really seeing here is a mashup. It's a kind of a blend of data from multiple frames, even has causal order issues. The middle and the right don't have those problems. You can see how much better they are. The middle one estimates the time using the server clocks on our system. The right-hand one extracts the time directly from the GPS data in the synchrophasor measurement. There you have to know the representation of your data, but you can get a perfect answer. So how do we do that? I want to just briefly give you a sense of it because it'll give you a feeling for how people build a system like this. So each Vortex shard, remember shard is one of these little replication groups, has 2, 3, 5, whatever number of servers we've been told to use in it. This has 2 each. There's a hashing rule for where data goes based on the name of the object. And so in comes data, and it gets put in the appropriate shard. If it had come in with a different name, it might have gone to a different shard. But we're thinking of it as a single data set. Multiple updates to the same name are the way we build up a log of the values as they evolve through time. When we do a computation, like a snapshot for that visualization or for an AI to query this data, a series of lambdas run, a series of pieces of AI run, triggering each other at that very high speed I mentioned. So they're going to look at this data while it's being updated. So we've got all these updates coming in, some to the same synchrophasor, some just landed on the same shard. Because the whole point is that this is like a file system, a massive file system composed of mini file systems. It's huge. Abstractly, when you ask for the data at a particular time, you sort of are talking about a time interval because of clock synchronization limits. And because updates are occurring, there's data that hasn't fully settled yet. For us, it takes about 50 microseconds. So this is the real picture. And now the question is, what should I show those lambdas? Arguably, I should show lambdas 2, 3, and 4 exactly what I'm showing lambda 1, or at least something consistent with it. And there is, in fact, a term for that. It's called a consistent cut, formalized by Leslie Lamport, working with someone named Manny Chandy. And that's what we do. So we wait until data is stable, 50 microseconds or so. We know how to detect that. Our protocols have that feature built in. When data is stable, we can do a snapshot along a consistent cut. And when a read, a get, occurs from one of these lambdas, it sees data on that consistent cut. And by the way, I said read, you might have been thinking, oh, there might be file systems here. We have a wrapper that makes our key value store pretend to be a normal file system. Prefer file system? It is. It also actually can prefer to be a publish subscribe thing called Kafka. You love Kafka? No problem. Pretend that we're Kafka. So what we saw here actually are pretty old ideas used to fix the HDFS issue. You can say, well, why didn't HDFS fix its issue? And the real answer is it doesn't need to. In the settings it normally runs, ML training, so much time elapses between an update and accessing that there's plenty of time for the data to stabilize. In our setting, with millisecond turnarounds, HDFS wasn't built for that. So it knows it's got the data, but it actually fetches the wrong version and it mashes stuff together. So let's look at some performance and then I'll take questions from you. This illustrates the vitally important task of assessing the condition of your cows. If you have a farm with about 1,000 cows, you might want to assess their body condition as they walk into the barn. It becomes challenging. We mocked up an AI for that. It turns out I got some funding from these people. So we built our very own, pipeline with visual components to assess body condition scoring. Ran it on a standard infrastructure, and then we ran it again on ours. Tenfold speed up. So hang on a second. Something popped up on my screen. There we go. So that'll give you some sense of what we're after here. We get higher throughput across the board than existing solutions. Scaled it out in different ways. We continue to do better. It wasn't that we starved the standard solution for resources. It was that it really wasn't trying to work on latency. It only cared about throughput. Throughput was high, but if you care about delay, it was terrible. Here's another example. Suppose that I set myself up in a city and I want to try to identify dangers associated with this intersection. Bunch of cameras, and I'd like the AI to continuously detect near incidents. Then I'm going to try to do something about the layout of the intersection. Well, what we're seeing here is that the identical AI, here's one of these pipelines, it actually has one of these branches for every moving object present that it identifies. So this guy identifies objects in the frame. I don't know why the camera is facing the wrong way. It identifies objects in the frame, and then for each object, the red thing predicts where it's going to go, one AI, and then the blue one asks, could this cause a collision relative to something else? And it tries to run in parallel with the red and with the green. So down here on the right, you can see a Vortex deployment, actually a cascade, but don't worry about that part. And you can see time spent in green. White gaps tend to be capture data or move the data. That's Vortex. And then red and blue would be the trajectory projector and the collision detector, which have to run in milliseconds, and we do it in milliseconds. So you can be pretty quick and say, up there on the right, somebody could wear one of those HoloLenses. Do that on Azure the way they recommend that you serve AI on Azure, seconds for each frame. Over here, you can see how many things we're moving on the left. You might be surprised that it doesn't scale worse. That's because image is actually a pretty fast kind of AI. Vision is fast. This illustrates Kafka, which is a pub-sub sort of store and forward architecture, but it also has a non-stored version. This is actually not even the storage version. What it's showing is end-to-end delay between two components. Vortex is orange. Kafka is the grayish blue. This is a logarithmic scale, factors of 10 for each tick, different object sizes, and 1 or 3 replicas being notified, right? Because you scale these things out that way. Vortex, nice and tight. The median is the circle, and then we get the 95% confidence range. Kafka, very big delays, tail latency, factors of 100 or 1,000, because after all, as I said, each tick is a factor of 10. Milliseconds versus seconds. Here is the 2 pipelines I mentioned very early, pre-FLMR. One of them is on TorchServe. That's the very poor throughput over here. Ray gets high throughput. We get a little bit higher throughput, queries per second. And then you can see different cases, whether it was running as a monolithic deployment, light blue, or whether it was running broken into pieces. And actually for us and for Ray, you can run it both ways, and we tried. Okay, and we actually can configure as a model server or as a sort of a microservices architecture. Here's the one that did sensing of speech. And again, we're matching on throughput, but it turns out we're killing on latency. So this is my last data graph. What I'm going to show you here is on TCP versus RDMA for one of the cases. Don't worry about which one. Ray is on the top. It's the blue. And then Vortex is yellow and red. Now this one is latency. So it's the same case we were talking about over here. Those tight latencies. Well, this is where we're passing data between stages of one of our microservices, not using the Kafka API, but that wouldn't have changed anything. And what you can see is that latency for Ray is higher and very, very widely varying. This is because RayServe, which is what we used, was built from Ray, and Ray optimized for throughput and batching. Vortex does a lot better even on TCP. That's the orange. Now, of course, when it overloads, it switches to heavily batched and you start to lose your real-time characteristics. And way at the bottom, this is us on RDMA, specifically on Rocky. RDMA over converged Ethernet. And now we're getting really, really tight distribution. And you can see that until it starts to backlog, very flat latencies that are quite low. And what we were varying there is how fast the data was coming in, queries per second. So it's latency for the average query as a function of the load on the system. This looks at a case with multiple different workflows, multi-tenancy on the same cluster. Because after all, if you're Mayo Clinic, you're not going to just use it for one doctor, right? And what it illustrates is that when you have these different modes of data, the type of scheduling you do is quite important. In this particular example, the different colored bars represent different pipelines. Some of them have visual components, the green one. Some of them are purely text, and they run for different amounts of time. That's enough to confuse traditional schedulers, it turns out, and I have a few of them: just in time, heterogeneous earliest finishing time first, random hashing. So when they spread load over a set of components, they make poor choices. Vortex, which has a scheduler of its own, we call it Navigator, is able to get much more fairness. So what you're looking at here is how big a penalty did the scheduler and the sharing impose relative, how much of a slowdown relative to if you had been the only thing on that cluster. So you want a small slowdown factor. And what you see, it's not uniform. People are out to get the 3D perception thing. It suffers under light load and a lot under heavy load. So those heavy visual kinds of tasks, which actually are pretty fast if you're smart about them, are being penalized, and quicker text tasks, as it turns out, are sneaking in first. Actually, I shouldn't say quicker, because actually the tasks may be quite slow. This has to do with how much slowed down they experienced, not how fast they are in absolute terms. So what you're really looking for is a scheduling discipline that across the board doesn't penalize much for these different tasks. And you can see that Vortex, over this mix of four tasks, none of them suffer much under light load or even under heavy load. Other common scheduling disciplines used in some of the systems I was mentioning, the real-time characteristics fall apart. And it turns out Navigator, for this mix, was able to not just get better scheduling, but a better placement of activity to resources that halved the amount of resource of servers that was needed. So I'm going to stop here and take questions. In summary, got this powerful framework. It's open source, very big performance wins. And as the trends bring us more and more of these kinds of ML pipelines, I think this is what you're going to want. Let me just mention the key people. Alicia Yang is amazing, and she's the lead developer on Vortex. Weijia Song was the lead developer on our storage layer, Cascade. He's now at a hedge fund. TC Wan, Ben Landrum, I won't read all the names, are all big contributors, although not quite at the level of Alicia. And we're very grateful for those who have funded us. So with that, let me take any questions for a maximum of 6.5 minutes, because then I have to go pick up my wife and I wouldn't want to be late.
Ahmed, do you want to go first?
All right. Yeah, let's open the floor for questions. Yeah, Paul, go ahead.
Ken, can you describe a bit more what a consistent cut is? People refer to that, and I find myself having deep disagreements with Leslie Lamport about how that was developed. But there is a computer science kind of like description. I thought you might be the best person to describe that.
Sure. Okay. So I'm going to use terminology I think Paul knows well, but maybe not everybody does. So first of all, let's just talk about causal ordering. One of Leslie's very big contributions was from physics, and it's the idea that one event can only really be said to be prior to another event if information could have flowed from one to the other. So Leslie did event cones similar to physics, Physics, they do this all the time. And he arrived at a way to represent the potential causality relationships in these systems, a way to put a special kind of timestamp on events as they occur, such that if A could have caused B, then A will be earlier than B. And there's a very concise representation, which is only a one-way implication. And then there's a fancier vector representation, which actually has a dual implication, where if A is less than B on these timestamps, if and only if A had an information flow path to B. Now, if I take pick a time within my time window and take an event, we can ask if somebody else querying the system at the same time would see not just that event, but other events that might be causally prior to the event and could have caused it. And let me give one quick example. Suppose that I'm hired by Paul. His HR person creates a record for me, and then in other subsystems, they create a payroll record. They create key entry swipe records, right? Those records depend on the first record. So that would be a causal relationship. Of course, sometimes causality is specious. It just happens to look that way. That's why Leslie calls it potential causality. But the idea, at least, is that it wouldn't make much sense to see the key swipe record and no record of this employee existing at all. So that would be a gap in the causal history of a snap. And so now if we think about, what events should be shown to somebody querying a system at time 10 a.m., once we pick one of them, we may have a choice of other events that are all within the clock synchronization window for 10 a.m. And what consistent cuts say is pick ones under a deterministic rule, but such that you never omit something which potentially caused something else. So when you compute on those events on that cut, if you see that Berman is swiping in the machine room, you're definitely also going to see, if you go and check, that Berman is an employee. Okay, and otherwise, these little race conditions can cause real confusion. They can cause phantom deadlocks. They can have me seem to be breaking into the machine room when Paul just hired me 5 minutes ago, things of that type. So that's the idea. There's an algorithm for it. It's not an expensive algorithm to run, but it's a little complicated to implement. And we've built that into our system.
Thank you. Oh, great answer.
So Ken, a quick question, like to clarify on this, like the cause, like I mean, this is only for events that they are cause based. But let's say if you're doing,
Well, we can't detect that, right? Because that's a semantic property. Who knows whether event A created a log record and event B depended upon that record. So we don't have a way to know that without knowing semantics. But we can see that information could or could not have flowed in the system.
I was just trying to find what are the exceptions on this. Like, let's say when you have, let's say, distributed database and there are things that are changing, they change from some. I mean, it's very interesting. It's like kind of like
Yeah,
an
no, it
absolute
is interesting.
limit.
But so suppose that a judge came to you and said, you got a phone call from your friend at Google, and you dumped stock. You sold all your Google shares. That was insider trading. And you
Mhm.
say, no, my friend, we were coordinating babysitting. It had nothing to do with Google. So potential causality doesn't mean that there was real causality.
I see, I see, I see. There was a channel, but not necessarily
There
had the
was a
information.
channel. That's right. Now, conversely, you could say there was absolutely no contact between my friend and me. They did not phone me. I did not get email. I did not get a text. You can look at my devices, and that might protect you in front of a judge that was open-minded. Different type of judge might say, I don't know, it's damn suspicious. So it's not a certain, because you only can talk about what's visible to a system. But potential causality is this idea that if I'm going to take a snapshot where some of the data comes from different servers, at least I don't want holes in the past,
Yes,
actual gaps.
interesting. All right.
Anybody else? All right, my wife awaits, so I'm gonna call this a
Beautiful.
success and hope
Beautiful.
everybody finds it interesting. Now, I will say it is open source. We just finished our first paper on the system on Vortex, but there are papers on all sorts of other pieces of it.
Mhm.
We're submitting the paper to a conference. We will make a public version of it available soon, but we haven't yet. So reach out to me if you want to see a copy of that paper, but you can read plenty of related stuff on my website. Okay,
Wonderful.
and with that, let me just thank everybody. And I see David's on there. David, yes, it can be used for academic projects. And we'll call that quits for today. Thanks, everybody.
Thank you, Ken. All right, we'll see everyone in 2 weeks with a talk by Med. All right, bye
Really great
everyone.
work, Ken. Thank you. Appreciate it.
Bye-bye, everybody. And by the way, I apologize for the a couple of weeks ago I was scheduled, but there was a family emergency and it was just impossible. So
No worries. Yeah.
No
Thank you.
worries.
Hope it
We're
didn't
glad you
continue.
presented today.
Yes.
Okay, bye-bye, everybody.
Bye, everyone.